Okay, so we've studied functions of several variables. We've looked at the limit of functions of several variables. Now we're going to look at the derivative. We're going to talk about what it means to differentiate a function of several variables. Now I want to go back just to refresh your memory about how we define the derivative in a function of a single independent variable. So if we've got a function, f of x, and we want to talk about the derivative of that function, we could write it this way. Of course, this is y equals. We could say that this is equal to, and we could denote this as f prime. It's equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. And this is how we define the derivative, and this is what the derivative is. Here we have the Leibniz notation, and here we just have the prime notation. And remember what this was about. We said that if you've got a function, this f of x function, and you want to find the derivative at maybe this point right here, I'll call it a, we said this, that you could talk about this point being a f of a. That's the point on the graph. And then we have another point over here, which is a plus delta x. And this, of course, would be a plus delta x and f of a plus delta x. And we talked about the slope of that secant. So if we're taking the slope of the secant, it's just going to be the change in y's over the change in x. And the change in x, of course, is just delta x. And if we want to get the slope of the tangent rather than the slope of the secant, we just let the distance between these a and a plus delta x go to 0. And we said, okay, that is the derivative of a single, when we're just dealing with a single variable. So we just talk about the derivative f prime of x. But now we've got two independent variables. So we've got the function f of xy, maybe z equals that. And we want to talk about that function, that derivative. Well, this is where we introduce what's called a partial derivative. And the idea is we're going to treat each variable in turn as a constant. So, for example, we might talk about the partial. So this is the symbol for partial. The partial of z with respect to x. And the partial of z with respect to x means we keep the y constant, we treat it like a constant, and we just find the derivative. So this would be, another way to write that would be f with a little subscript, x and y, like that. Now, as far as the definition, it's going to go like this. The definition of a derivative, the partial of z with respect to x, we're still going to have a limit, and we're going to have the delta x going to 0. But the function is going to look a little different because we're going to have f of x plus delta x, comma y, minus f of xy all over delta x. And this is how we're going to define the partial of z with respect to x. Now, we also have the partial of z with respect to y. Okay, so let's look at that one. The partial of z with respect to y. Okay, and that's going to be written this way. And now we're keeping x constant and just differentiating with respect to y. So now the definition is going to look like this. dy, the limit as delta y goes to 0 of f of x, comma, y plus delta y minus f of xy over delta y. So there's the partial of z with respect to y. So right now, we're just defining the derivative, defining these partials, and just looking at some, we're going to look more at this notation here in just a second. But I want to look at a specific function with two independent variables, and just to show you how this process works. So let's look at this function. Let's suppose that we have f of xy equals 25 minus x squared minus y squared. So we've got this function, and you may recognize that as a paraboloid. It goes, it has a high point at 25, so it goes up. The highest z point is 25. It intersects the xy plane at, from the x being -5, at a circle. So it intersects the xy plane in a circle of radius 5. And I've got a picture of that, of the graph in Maple. Here, let me see if I can open up Maple. Okay. So here I've graphed the function. I've graphed another part of this. I've got, here is the paraboloid, you can see in blue. Now what I've done in addition to this is I've also graphed the plane y equals 3. So I'm looking at the intersection of this plane y equals 3 and this paraboloid, 25 minus x squared minus y squared, and you can see the intersection here. Now, the reason I did that is because I want to show you what, when we talk about partial differentiation, I want to show you a specific example of where we keep one of the variables constant. In this case, I'm keeping the y constant. And I'm saying, in fact, I'm giving it a particular value. I'm saying that y equals 3. And you can see that we have a nice intersection here. Now, if y is equal to 3, what I'm looking at is this curve here in blue. Just without any depth, just the blue curve that intersects there with the green. So let's go back here and look at this. Whoops, let's see here. Okay, so what we have is, we have this thing. Okay, so this is what I just showed you. And what I want to look at is this part. So this is when I keep y fixed. And when y is fixed, in fact, when y is equal to 3, this 25 minus x squared becomes 25 minus x squared minus 3 squared, which is 9. So now you could think of this as, you know, a function of a single variable. So we have this. We have f of x is equal to 16 minus x squared. And in fact, what we're looking at is this thing. We're looking at this curve right here. And now, if I want to find the derivative, we know how to find the derivative. This is just f prime of x is equal to negative 2x. And this will give us the slope for any, for whatever tangent we want. So let's suppose I want to, we'll use this. We'll use f of 2, f prime of 2. F prime of 2 is equal to negative 2 times 2, which is negative 4. So what we get is that is the slope of that tangent right there. If we were to draw a tangent, that would be the slope of it. Now, what I want to do is show you how we would approach this problem without setting y to any particular value. If we didn't set y to a particular value, then we would have this. We would have the f of xy equals 25 minus x squared minus y squared. And I would talk about the partial with respect to x. And this would just be negative 2x. Now we could also talk about, so I'm treating y in the same way I treat 25, just as a constant. It's not a variable anymore, it's a constant. And then I could do the partial with respect to y. And that would be negative 2y. Now, so this is how we engage in partial differentiation. Now, there are other things that we can do. For example, we can talk about higher order derivatives. Let's suppose that I wanted to get the second derivative. Well, I would just put another x there, and I would get -2. The same over here, I could have y, and I get -2. Now, it's these higher order derivatives that in the notation that we use for these higher order derivatives that I want to focus on now. So let's suppose I've got some function. Let's suppose f of xy, and we'll just say x cubed y to the 4th, something like that. And I want to talk about the partial with respect to x. Okay, the partial with respect to x is just going to be 3x squared y to the 4th. So y to the 4th is just like any constant that would be attached. If instead of y to the 4th we had 2x cubed, then I would have 3x squared times 2. Now, we can also do the next derivative, just like we always have. I can take the next derivative, and in fact, I'm differentiating this, and I'll get 6x y to the 4th. So there's the second derivative. Now, I want to use this other notation here. So here's what we've got. This is the partial of z, or I could say, I'm saying z is equal to this. We could have partial of f, but with respect to x, that's what that is. And this right here, think about this now. If we've got partial of z with respect to x, and we want to differentiate that again with respect to x, intuitively you would think this notation goes like this, and then dx squared, and you'd be right. This is how we're going to use this notation. This indicates the second derivative of z with respect to x. So this is z like this. There it goes. Now, because we have two variables, we could do what's called mixed partials. So let's go back, and we've got our function here. It's let's see, it's x cubed y to the 4th. Okay, so we have f of xy equals x cubed y to the 4th. And now I want to do this. I want to, once again, I'll take the first partial. So I've got partial f with respect to x, and that's 3x squared y to the 4th. Now I want to do something different now. Instead of taking the partial again with respect to x, I'm going to take the partial with respect to y. So here's what I have now. I have, and by the way, this is f like this. So now I want to take the second partial with respect to y. So what I'm going to do is, I'm going to take the partial with respect to y of the partial with respect to f that we just did. So I'm going to take the derivative of this thing that we just did. And look how that's going to look. That's going to be this way. So notice there's the partial y, partial x. And notice what we took the derivative of first. We first of all with respect to x, and then with respect to y. So we're reading from right to left instead of left to right. But that would be this. It's going to be 12x squared y to the 3rd. And over here, that would be xy. Okay. So notice that this and this are telling us the same thing. With this, it's a little more intuitive. You know, you differentiate it with respect to x first and then with respect to y. Here you're kind of going backwards. But that's how we read that notation. Okay, now, see if I can scroll down. Okay. Now, okay, now let's look at something else here. Let's suppose, Now remember, we've got z is equal to f of xy, and this was x to the third, y to the fourth. That was the original. Now, let's do this. Let's do partial of z with respect to x. Just like before, we've got 3x squared y to the fourth. And then, we did partial of z with respect to, we did the second derivative. Okay. So we've got the second derivative. Okay. So the second derivative and we found that to be 12x squared y cubed. So I just kind of rehashed it. Now, let's go the other way. Let's take the partial of z with respect to y. And that would give us 4x cubed y cubed. There's the partial with respect to y. Now what I want to do is I want to take the derivative with respect to x. So now here I go. I've got this. I've got the second derivative, and now I've got y here and x here. So now I'm going to take the derivative with respect to x. And actually goes back the other way. I did y first. So here I go. I'm going to differentiate this now. I'm going to differentiate this one. That's the derivative, the partial with respect to y. Now I'm going to take the partial with respect to x for this one. And this is going to give me 12x squared y cubed. Now, you'll notice that these two look the same. So this one up here was xy, and this one here was yx. And they're the same. So these are the same. And that's one of the properties of these mixed partials. You're going to get the same thing whether or not you differentiate with respect to x first or with respect to y first. So that's something that we want to keep in mind. It might at times make things simpler for us. Now, one more thing I want to mention is let's suppose that we don't have two independent variables. Let's suppose we have three. So maybe we'll have something like this, f of x, y, and z. Well, we can talk about the partials of that derivative as well. We can talk about the partial of w with respect to x. And the notation's the same. And the definition looks the same as well. So this would be f of x plus delta x. Now the y is constant and the z is constant. Okay. So there's the partial of w with respect to x. We can do the partial of w with respect to y. Same notation. Except delta y now. Delta y. There we go. Let's see here. Delta y. And one more, the partial w with respect to z. This time as delta z goes to 0. X and y are held constant. There. So we can define the derivative for functions with more than two independent variables. And here we have it for three independent variables. Now, what I want to do is just look at an example very quickly. of a function with 3 independent variables. So let's suppose that we have this situation here, and let's suppose this is equal to x squared plus 4xy plus z squared. And I want to get, first of all, the partial of w with respect to x. Well, I'm holding everything constant except x. So I differentiate this term and I get 2x. I differentiate this term and I get 4y, because y is just a constant like that 4. And then this term gives me a 0 for the derivative. So there's the partial of w with respect to x. Now let's look at the partial of w with respect to y. The only term with a y in it is this one, and it's just going to be 4x, because 4x is like the constant. And then we've got partial of w with respect to z, and that would just be 2z. This term is the only one that matters, because the others just terms of constants.